Functional forms for regression. In order to apply a regression model, the relationship between the dependent variable and independent variable must be linear. Now, if the independent and dependent variables are not linear, then either the independent or dependent or both must be transformed such that their relationship does become linear. So let's look at the first scenario, and each of these scenarios examines the format for both the independent and the dependent variable. So in the first case, we're looking at ln, and in this case, y, or the dependent variable, is a linear function of x. So this relationship may be expressed through the following regression format. So there it is, y as a function of x. Let's do an illustration. Suppose that the consumer income, which would be the dependent variable, is equal to 9,000, so that would be your constant, plus 20, that will be your beta 1 coefficient, times the average hours worked per year. So let's make sure we can understand this on a conceptual level. Of course, the more hours an individual works, the more income that the consumer will have to spend. So note that if the consumer does not work during the year, then their income would be 9,000. So algebraically, what that means is if this is 0, then this whole thing disappears, and therefore their consumer income will simply be 9,000. And in real life, where is that 9,000 coming from? This will be through like Social Security benefits. However, for each extra hour worked, so for every plus 1 hour, we would multiply that by 20, and therefore consumer income will increase by $20. Now in the second scenario, we have log ln, and what that means is that the logarithm of y is a linear function of x. Now tip, logarithm implies percentage change. So that's what logarithm is. It's percentage change measured in continuously compounded format. So starting from our standard linear regression equation, which is right there, all we're going to do is we're going to say, well, now the dependent variable is in log form. In other words, we're looking at the natural logarithm, or the percentage change in y is a function of x. Let's look at an example. Suppose that sales is growing at a constant rate over time. So change in sales is exponential, meaning it's nonlinear. And you can see why that is. So if the percentage change is the same each year, that means the dollar change each year will get bigger and bigger and bigger, because the base value is getting bigger and bigger each year. So the same percentage change on a bigger base value translates into a larger dollar change. But then that wouldn't be linear, it wouldn't be constant. So what we would do is we would take the logarithm of sales. In other words, we're measuring the percentage change in sales, because that's what's constant. Let's do an illustration. Suppose that the ln of sales, and again, ladies and gentlemen, the best way to think of ln of sales is in percentage terms. So I know for a lot of us, maybe we haven't seen calculus or algebra in a long time. So when you see logarithm, just substitute it with percentage change in sales. So that's all we're saying. So percentage change in sales is equal to 5.7 plus 0.08 times the time, or the period in which you're looking at. So therefore, if we're asked to calculate sales after 20 years, here it is. So here's our regression framework expressed as a log linear format. Again, here's the log, here's the linear. And so we just plug in the values. So we're looking at 20 years out. So we solve for this. And then what we do is we take the e of both sides, or the exponential on both sides. And what happens here is the e and the ln cancel out. And over here we get e to the power of 7.3. And when you punch that into your calculator, you get $1,480 for sales. So note, again, ln of sales measures the cumulative percentage change in sales, compounded continuously. This beta 1 term of 0.08, that's the percentage sales per year. So what we're really saying here is that the cumulative percentage change in sales is equal to a constant plus the percentage change in sales each year times the period for which you are trying to forecast sales for. Now, the discrete growth rate may be found as follows. So the relationship between continuous compounding and discrete is as follows. It's expressed through here. So e to the power of x is equal to 1 plus r. And the difference is that the x is continuous compounding, where the r is the equivalent, but without compounding. In other words, what would be the percentage change or the equivalent percentage change assuming no compounding? So since we're given the continuously compounded percentage change, we plug that in there, and then we solve for r, and then r equals to 8.33%. So in other words, there's two ways of expressing sales growth per year. We can either say sales is growing at 8% compounded continuously, or equivalently, we can say that sales is growing at a discrete growth rate of 8.33% per year. It's the same thing. Now note 4, since the ln of y is different format than y, so remember this is the ln of y, whereas this is just linear y, so they're completely different format. And in our example, this would be sales, whereas this would be percentage change in sales. Completely different. One's in dollars and cents, measures sales in absolute terms. One is rate of change, which is in percentage terms. So since they are in completely different formats, we cannot compare their statistics, such as their R-squared, standard error, and f-stat. So in other words, we can't look at a log-lin model and lin-lin model and look at their R-squared and say, okay, which one's better? They're not even comparable. It's like apples and oranges. Now the third format is what's referred to as lin-log, and you have to remember the first term refers to the y and the second term refers to the x. So lin-log means that y is a linear function of the logarithm of x. And again, ladies and gentlemen, if the term logarithm throws us off, let's just substitute it with percentage change. That's all it is. What's the twist? It's percentage change in sales compounded continuously. So again, starting from our basic regression framework, how do we tweak this, which is basically lin-lin, so that's our default regression format. How do we tweak this for lin-log? No problem. So remember, the first term refers to y, so we don't have to make any adjustment, but the second term refers to the x. So rather than putting a linear format for x, we take the logarithm of x, and that's it. That is it. So let's do an illustration of a lin-log model. So according to the economies of scale, as the company manufactures more units, the cost per unit should decrease. Except what's unique here is that when we say manufacture more units, we're measuring it in terms of percentage change in units produced, rather than absolute amount of units produced. So suppose that unit cost is equal to 0.7, so this would be our constant, minus 0.003, that would be beta 1, and then we're looking at the natural logarithm of the number of units produced. Again, if this throws you off, how do we substitute that? We're trying to find over here the percentage change in units produced. So we're asked to calculate the unit cost if the company is producing 500 units. So therefore the unit cost, it's right there, that's our dependent variable. So we bring down the constant, we bring down the beta coefficient, and then we just plug in the logarithm of 500, so that works out to that. And then when you get to the last step, you get unit cost equaling to $0.6813. So note or observations, you can see that unit cost is a function of the percentage change in units produced, and you can see that right here. Unit cost is a function of percentage change of production. Now for every 1% increase in units produced, so if this goes up by 1%, right there, so if this goes up by 1%, now what's the catch? 1% compounded continuously. So if it goes up by 1% continuously compounded, it's just algebra, ladies and gentlemen. You multiply that by negative 0.003, and therefore unit cost drops by $0.003. It's right there. Third observation, the results of ln-log are comparable to ln-ln, since in both cases y is expressed in linear format. And you can see that right here. Remember what I said? The first term refers to y. So you can see that y over here is expressed in the same format. So therefore we can compare the statistics resulting from both formats. So for example, we can compare the r squared of a ln-log to a ln-ln, and then we would conclude that of these two models, the one that has the higher r squared has a better explanatory power, because now they're comparable. The last scenario, as far as formatting is concerned, is referred to as log. And remember what log means. Log is percentage change. So there it is. The percentage change in y is a linear function of the percentage change in x. And again, ladies and gentlemen, have a look at my approach. I always start from the ground floor. And what I mean by ground floor is, what is our default format for a regression? It's right here. Y is a function of x. So when you tell me log, and I know that log is just percentage change, all I do is I replace the y and the x with their natural logarithms. So the logarithm of y is equal to b0 plus beta 1 times the logarithm of x. Let's do an illustration of a log-log model. Suppose that the price elasticity tells us how sensitive the percentage change in quantity is to the percentage change in the price of the underlying product. And suppose that from our observations, we note that the logarithm of quantity, in other words, the percentage change in quantity demanded, is equal to 0.07 minus 0.2 times the percentage change in price. So do you see what we're doing here, ladies and gentlemen? Rather than measuring quantity and price in absolute terms, we're measuring these variables in percentage change terms. So we're saying, what percent will quantity change if price goes up or down 1%? And there it is. For every 1% increase in price, so there it is, 1%. And why are we measuring it in percent and not dollars? Because I see logarithm there, and I know that logarithm measures percentage change. So if the price goes up by 1%, 1 times negative 0.20 would mean that this would drop negative 0.2%, and it's right there. So conclusion, we select the functional form that best fits the data. So really it's up to the analyst's discretion to determine which of those 4 formats to use. And the guiding principle is use the format that best fits through the data. And what we mean by best fits, we mean that it best explains the observations. So therefore, the model that does best explain the observations would have the lowest standard error. That makes sense, right? So the better you explain the data, the less errors there will be. It'll have a higher R squared. In other words, it'll explain a greater proportion of the total variation. And at the same time, it'll have a high F-stat, meaning that the regression will explain more of the variation than the errors will. And at the same time, the errors should be random and normally distributed. So the model that the analyst will finally select would fit all these conditions, or I should say will satisfy all these conditions.